In this video, we look at how a catalyst can change your reaction rate and what it does with activation energy. So in the last video, we looked at the 3 ways that you can increase the rate of a reaction by either increasing the surface area of the thing that you're reacting, by stirring it, or by heating it up, right? By increasing the temperature, okay? There's actually another thing you can do, and that is by actually adding a different substance to the reaction, by adding a catalyst. And this can actually increase the reaction rate. A catalyst is going to be a substance that increases the reaction rate without being consumed in the reaction. Okay? So it's going to help the reaction happen faster, but it doesn't actually get consumed in the reaction itself. Right? And what that really does, okay, the way that it's able to increase the reaction rate is catalysts lower the activation energy. Right? This is how a catalyst is able to make a reaction happen faster. It lowers the activation energy required. Okay? And there's 2 main ways it can do that, basically. Way number 1 is that it reacts to form an intermediate. Okay, if you go on to take organic chemistry, you are going to talk about intermediates a lot. All right, but it can react in my chemical reaction to form an intermediate, which then has a lower energy pathway, aka a lower activation energy. All right, so what this would look like practically is if you had an uncatalyzed reaction, you might have something like X plus Y reacts to make the compound XY. Nice little synthesis reaction, right? 2 reactants, smash them together, you make a product, okay? If, however, you had a catalyzed reaction, you might have X plus C. C stands for your catalyst, right? Making XC. This is your intermediate product. Then you have XC reacting with Y to make XY and C. Okay, so you get a synthesis reaction here where X is going to, part of your reaction is going to connect to that catalyst, and then you have a basically single replacement reaction, right? Y swoops in, kicks the catalyst off. The catalyst never got consumed by my reaction, and I got the product that I wanted in the first place. And by making this intermediate, I'm lowering the activation energy, depending on what the catalyst is. Perhaps, even though this is 2 steps, sometimes this is an easier thing to do. It requires less energy than overtaking whatever activation energy it was from this first uncatalyzed reaction. Okay, so that's one way it can make an intermediate. The other way that this works, it provides a surface for the reactants to be in a specific orientation. Okay, and the way I always think about this is with Pac-Man. It's beautiful, I know. Okay, all right, so if I had, for example, these are my 2 reactants, and I need them to react to combine together, the synthesis reaction, okay? They need to be oriented the correct direction, and they need to collide with enough force to be able to actually overtake that activation energy, okay? They might be flipping around, hitting each other any which way. If I have a catalyst, okay, that provides this surface that they are attracted to, okay, this guy can kind of swoop in and, oh, yay, he's super attracted to that side. This guy is attracted to this side. Boom. and then they fuse together, right? Or they combine together, their chemical reaction happened, they bonded together, and then I get my product, okay? This might be much faster, has a lower activation energy than if these two guys were just floating around out in empty space, hoping to connect randomly, right? And to collide with enough energy and to collide with the proper orientation, okay? And we have an energy diagram for our catalyst, all right? This is time, energy, all right? Okay, so if this was my random reaction pathway, okay, my random reaction energy diagram, okay, you should be able to tell this would be an exothermic reaction, right, because products are lower than the reactants. All right. But if this was my regular reaction, okay, so it would be my regular pathway. Okay, what a catalyzed reaction is it would reduce the activation energy required. So the reactants start at the same place, but when it starts to go up, it's a much gentler slope to overcome, okay? And it ends up in the same spot. So my green here would be my catalyst added, all right? So I have less activation energy to overcome than I did before. It lowers the amount of activation energy I need, which means my reaction is able to happen easier, right? I don't have this giant hurdle to overtake. I have a smaller hurdle to overtake. All right. Hopefully that makes sense in general, right? The whole purpose of this is to lower the activation energy. Okay, so it lowers the amount of activation energy required, and catalysts are really important in our bodies. Okay, catalysts are extremely important. There's catalysts that are, in our heart that help our heart beat and pump blood. That, without the catalyst, those reactions would happen too slowly, and we wouldn't be able to actually have our hearts beat. There are a ton of catalysts and enzymes that help break down food in our digestive system, which is very important. That's how we get energy to, talk on these wonderful videos to you, to talk with our hands because we're Italian, to, do anything, to breathe, right? We need that energy. So in order to get that energy, we need the catalysts, the enzymes to break down our food, to digest. It's an incredibly important thing to make sure you have catalysts, to make sure you understand the catalysts make reactions happen faster, happen easier, lower activation energy.